executing a computation that would have been impossible on a classical machine. It's crazy to think about, but that statement right there, it's not science fiction anymore. It's actually the very real benchmark for what we call quantum supremacy, or quantum advantage. For decades now, our traditional computers have been on this incredible exponential trajectory of improvement, but they are finally and undeniably hitting their absolute physical limits. We are standing on the edge of a fundamental shift in how we process information, one that promises massive, sometimes exponential speedups for some of the absolute hardest problems on Earth.
Welcome to this explainer. Today, we're going to cut right through the hype and unpack the reality of quantum computing, specifically looking at its massive, game-changing potential for the financial sector. We'll explore what's actually happening in the research labs right now, where the hardware currently falls short, and exactly why major financial institutions are already racing to harness this tech.
So here is our roadmap for today. We'll start with 1, the quantum computing revolution. Then move into 2, the science of qubits. 3, the challenge of quantum noise. 4, transforming financial services. And finally, 5, preparing for the quantum era.
Let's dive right into Section 1, the quantum computing revolution, beyond zeros and ones.
Okay, so our global financial institutions rely heavily on some incredibly complex mathematics. We're talking specifically about something called combinatorial optimization. This is the math involved in calculating risk, managing massive portfolios, and optimizing thousands of trades. The major problem here is that these problems scale exponentially. Every single new variable you add doubles or triples the complexity, and classical machines, which process information in a strict, rigid binary of zeros and ones, eventually just hit a computational wall. They literally cannot process the sheer volume of possibilities fast enough. But quantum computers? Well, they leverage quantum mechanics to process information entirely differently. They completely shatter that wall, providing exponential power for these massive mathematical headaches.
That brings us to Section 2, the science of qubits, how it actually works.
To pull back the curtain here without getting totally lost in the advanced math, think about solving a maze. A classical computer is basically like a very persistent but completely blind mouse navigating that maze by trial and error. It runs down one path, smacks into a dead end, turns around and tries another. I mean, it works, but it's incredibly slow. Quantum computing, on the other hand, acts like smoke filling that entire maze all at once. As the computation runs, the paths that lead nowhere just fade away, while the route to the actual solution is naturally reinforced. It doesn't just do what a classical computer does, but faster. It's taking advantage of completely different physical principles.
And that smoke analogy brilliantly illustrates our first key principle, superposition. See, a classical bit is always either a 0 or a 1, period. But a quantum bit, or qubit, can exist in this richer state containing multiple possibilities simultaneously before it's actually measured. Imagine flipping a coin. While it's spinning in the air, it isn't strictly heads or tails, right? It's kind of a blur of both possibilities. Only when it lands, or is measured, does it collapse into a definite outcome. Because of this superposition, just 10 qubits can represent over 1,000 states at once. And 50 qubits? That surpasses 1 quadrillion states. It's mind-blowing scale.
But what happens when you link these qubits together? That brings us to entanglement. When 2 or more qubits become entangled, they're essentially locked together as a single quantum system. The state of one qubit directly, instantly relates to the state of the other, forming this unified processing powerhouse. They share correlations that classical physics simply cannot explain, which allows the computer to process complex algorithms in ways that are literally impossible for traditional machines.
Finally, we have interference. In basic physics, we know waves can reinforce each other to grow larger, or they can cancel each other out. Well, a quantum computer uses this exact same principle, but with probability amplitudes. Through interference, the quantum algorithm naturally reinforces the correct answers and cancels out the incorrect ones. Going back to our maze analogy for a second, interference is exactly what amplifies that most promising path through the smoke, while all those wrong paths just quietly disappear.
All right, let's hit pause for a reality check in Section 3, the challenge of quantum noise, the NISQ era reality check.
The harsh reality is that qubits are unbelievably fragile. Any unwanted interaction with the outside environment, we're talking minor vibrations, heat, even background electromagnetic noise, completely destroys their superposition and entanglement. This is a phenomenon known as decoherence. To prevent this, many quantum systems have to be cooled to near absolute zero. That is around minus 273.15 degrees Celsius. Just to put that into perspective, That is significantly colder than the deep vacuum of outer space. So, yes, it is incredibly difficult to build qubits, but it is infinitely harder to protect them, manipulate them, and measure them without destroying the incredibly delicate information they hold. Because of this extreme sensitivity, we are currently living in what researchers call the NISQ era. That stands for noisy intermediate scale quantum. We do have intermediate scale computers today with 50 to 100 qubits, but they're noisy. The physical error rates in the hardware right now are much, much higher than in your conventional electronics. At this moment, a quantum computation is so delicate that even a microscopic change in temperature or a stray magnetic field can scramble the data entirely and spit out the wrong answer.
And the hard data paints a very strict mathematical boundary here. If you plot the tolerable physical error rate against the size or the area of the quantum circuits we're testing, you hit a literal wall. There's a hard limit. If your algorithm requires a circuit that sits above that limit, the quantum noise is simply going to overwhelm the calculation and ruin your results. It vividly proves exactly how tightly our current empirical error rates constrain the size of the algorithms we can actually run successfully today, at least without needing massive, resource-heavy quantum error correction protocols.
So why bother? Well, let's get into Section 4, Transforming Financial Services, the quantum price.
If the hardware is so noisy and fragile, why is the finance sector so obsessed with it? Because despite the sheer difficulty of the NISQ era, early experimental systems are already actively testing three massive financial pillars that hold the highest potential upside: targeting and prediction, trading optimization, and risk profiling. These are the specific areas where the mathematical complexity skyrockets so incredibly fast that classical computers are currently holding the entire industry back. Let's break down exactly where classical systems are completely failing today versus the exponential speedups that quantum computing promises. Just look at fraud detection. Right now, classical systems return an astonishing 80% false positive rate. 80%! That is costing billions of dollars. Quantum algorithms promise superior, high-precision pattern finding to drastically slash those losses. Or take customer onboarding, which can drag on for up to 12 weeks just to ensure proper credit scoring. Quantum promises near real-time agility. And then in risk simulation, where classical Monte Carlo simulations are strictly limited by scaling estimation errors, quantum computers offer a quadratic speedup, allowing us to sample vast amounts of data in a completely different way.
But listen, this isn't just about making more money. It's honestly about survival and compliance. Overlapping regulatory frameworks like Basel III and its ongoing revisions are now demanding a much, much larger array of risk management stress scenarios. In fact, over the coming years, compliance costs are expected to more than double. Financial institutions desperately need the raw computational power to run these massive stress scenarios quickly and accurately. That makes quantum simulation capabilities an absolute necessity if you want to shield your firm against massive regulatory penalties.
Which brings us to our final part, Section 5, Preparing for the Quantum Era. The action plan.
Here is exactly what your institution needs to be doing right now. The industry consensus is totally clear. You cannot afford to sit around and wait for perfect, error-free hardware. Step 1 is to appoint quantum champions within your organization to start experimenting today. Step 2 is to test currently available quantum algorithms, things like AI classifiers and option pricing simulators, which, by the way, are already accessible over the cloud. And step 3 is to partner up. You need to connect with like-minded institutions, application developers, and the broader quantum ecosystem so you can gain end-to-end access and real practical experience. I want to leave you with this final, rather provocative thought to chew on. The institutions that adopt quantum computing early are going to capture a massive arbitrage advantage, meaning they'll be running calculations that are literally impossible for their competitors to perform. So ask yourself, will your organization seize this impossible arbitrage potential early? Or will you stand by and watch traditional computing render your firm completely obsolete? The choice, and frankly the future, is in your hands. Thanks for joining me on this explainer, and keep learning.